Desde milenios atrás, el cáncer ha sido uno de los padecimientos más terribles de los seres humanos. Y a lo largo de la historia, la ciencia ha buscado entender qué es el cáncer y cómo curarlo. La ciencia avanza, y con ello nuevas propuestas y tratamientos surgirán, con la esperanza de que en un futuro cercano se logre ganar la batalla en esta larga lucha contra el cáncer. Por estas razones, la prevención juega un papel fundamental en el control del cáncer. Desde milenios atrás, el cáncer ha sido uno de los padecimientos más terribles de los seres humanos. Y a lo largo de la historia, la ciencia ha buscado entender qué es el cáncer y cómo curarlo. La ciencia avanza, y con ello nuevas propuestas y tratamientos surgirán, con la esperanza de que en un futuro cercano se logre ganar la batalla en esta larga lucha contra el cáncer. Por estas razones, la prevención juega un papel fundamental en el control del cáncer. Desde milenios atrás, el cáncer ha sido uno de los padecimientos más terribles de los seres humanos. Y a lo largo de la historia, la ciencia ha buscado entender qué es el cáncer y cómo curarlo. La ciencia avanza, y con ello nuevas propuestas y tratamientos surgirán, con la esperanza de que en un futuro cercano se logre ganar la batalla en esta larga lucha contra el cáncer. Por estas razones, la prevención juega un papel fundamental en el control del cáncer. Desde milenios atrás, el cáncer ha sido...
Bienvenidos al ciclo de conferencias Universidades por la Ciencia, organizado conjuntamente por Fundación UNAM y el grupo de universidades y centros de investigación en México y en el extranjero, en Estados Unidos, en el Reino Unido, Brasil, Argentina, Chile, España. Les agradecemos mucho el interés y que nos acompañen. Y el día de hoy tenemos una conferencia muy especial a cargo de la doctora Beatrice Pelloni, quien es profesora de matemáticas en la Universidad de Heriot-Watt en Edimburgo y del Instituto Maxwell para Ciencias Matemáticas. Es realmente un placer el tener a la doctora, quien es una de nuestras mejores especialistas y además una gran impulsora de los estudios en matemáticas. Es también la editora de los proceedings de la Royal Society en Edimburgo y tenemos ahora un tema de gran interés sobre uno de estos efectos en óptica extremadamente interesantes, el efecto. Welcome to the Universities for Science seminar series. This seminar cycle is organized by the UNAM Foundation and a group of universities and research centers in Mexico, the US, UK, Spain, Brazil, Chile, Argentina. The seminar cycle has been extremely successful, and we have participation from many different countries. And today we have a very special conference by Dr. Beatrice Pelloni, who is a professor of mathematics in the Heriot-Watt University and the Maxwell Institute for Mathematical Sciences in Edinburgh. We welcome and thanks Beatrice for this seminar. And Dr. Pelloni is a very well-known mathematician. She is the editor-in-chief of the Proceedings of the Royal Society in Edinburgh. And we are extremely interested in her research. We have a person from the University for Science Consortium making the presentation is Professor Kirill Sherednichenko from the University of Bath. Hi, hello, Kirill. And I'm extremely pleased to welcome all of you. We have the possibility of interacting with you through the different platforms. And thanks very much. And Kirill, please.
Yes, thank you, Jaime. Hello, everyone. I'm Kirill Sherednichenko from the University of Bath, and it's a special pleasure to introduce our speaker today, Professor Beatrice Pelloni from the Heriot-Watt University. Professor Pelloni is well known for her work on the qualitative behavior of linear and nonlinear PDEs of interest in mathematical physics, particularly boundary value problems, integrable PDEs, and general models of fluid dynamics. Beatrice got her PhD in mathematics in 1996 from Yale University. After holding a Marie Curie fellowship and a subsequent postdoctoral position at Imperial College, she became a lecturer, reader, and professor of mathematics at the University of Reading. She moved to Heriot-Watt in 2016, where she is currently professor of mathematics and head of the School of Mathematical and Computer Science. She has been a very active member of the UK mathematics community, having had various roles in the London Mathematical Society as part of the Women in Mathematics Committee, an elected member of the council, and as chair of the Research Meetings Committee. She has also served as chair of the Women in Mathematics Committee of the European Mathematical Society. She is currently an elected member of the Executive Committee of the European Mathematical Society and a sub-panelist for the Research Evaluation Framework 2020. This is an important exercise of assessing the quality of research carried out at UK universities, taking place every 7 years. She has presented her work at high-level international meetings and was the Olga Taussky Todd Prize Lecturer at the International Congress of Applied and Industrial Mathematics in 2011, and the London Mathematical Society Mary Cartwright Lecturer in 2019. She was elected Fellow of the Institute of Mathematics and its Applications in 2012, and Fellow of the Royal Society of Edinburgh in 2020. I'm sure Beatrice will share with us today some insights into her approach to mathematics and interdisciplinary research. So I guess I'll be stopping here and passing it over to Beatrice for her lecture on the Talbot effect or the phenomenon of dispersive quantization. Just one more note, questions are very welcome in the chat of the platform that you are using. And I pass over to you, Beatrice.
Well, many thanks to Jaime and to Kirill for this introduction, but much more for the tremendous honor to be invited to give this lecture. I'm really quite excited and a bit nervous about this. I hope that my English is clear for everybody, but please do stop me if not. And also that the talk, which I understand is a talk for a general scientific audience, is clear enough. I could have chosen several topics. I chose this because it's a topic I've been working on recently with both former PhD students, current PhD students, and collaborators from both a long time ago and new ones. And also because I think it's a topic that lends itself to be explained via pictures a lot. So hopefully something will stay with you after the talk, even if you don't understand all the mathematical details. Is not important. And it's quite, in some sense, it was a surprising effect to be found first time, and it continues to present surprises, both from the general phenomenological point of view and from the mathematical point of view. So hopefully it will interest you as it has interested me. I knew nothing about this until about 5 years ago, or maybe 6. And I'll tell you a bit the story of how I got involved. So first of all, why Talbot effect? And let me see if I can go on. Okay. So this is Mr. Talbot. He was a sort of polymath in the 19th century in England, not Scotland, unfortunately. Scotland had its share of many great scientists in the 19th and 20th century, and it's my adopted country at the minute, but Talbot was English and was interested, well, he was interested in many things, but one of the things that really gripped his attention was the possibility of fixing images, so taking pictures, photographs, we would call them now. He first worked with what was called the Camera Lucida, which was just a device for projecting a picture from outside onto paper so that one could trace it and reproduce it. But that didn't seem to be sufficiently, to reproduce sufficiently high detail pictures with the right colors. He wasn't happy about that. So for over many years, he kept coming back to finding a way to fix the images. He liked painting, but he also just liked the scientific challenge of trying to fixing images in some other way. And so the next thing he did was working with this, what's called the Camera Obscura, which was the precursor of a photographic camera. And it was one of, in fact, the first, as far as we know, to find a way to fix the image projected through this Camera Obscura on paper in some way. In fact, his is the oldest known photographic negative in existence. Is this thing here. It's very fragile. It cannot be exposed to light. I don't know how the photograph was taken. You can find it on the website, but it's not very often exposed to light because it would fade. And it is the earliest known photographic negative existence, and it's a picture of a window in the mansion in Devon where the Talbot family lived. Before he could patent his ideas, the French, who is credited with the invention of the photographic camera, patented his, which was a terrible blow to Talbot, but he continued, and he had a patent a few years later for a better system for fixing images. And this is a slightly later image. This is from 1840, so about 5 years later. It's the same type of picture of window that you saw in the previous negative. So he kept going all his life. He became a fellow of the Royal Society of London and very famous for his photographs. He took photographs of a lot of natural, plants and flowers, but also things like this big latticed windows in Lacock Abbey where he lived. And as he was doing all this investigation, he found something that surprised him. And he found that when light passed through a grating like the one in this picture, so the window had iron bars in it to reinforce it, at a certain distance from the window, this grating pattern was reproduced. So this is what he wrote about this. Okay, so he reported that he observed a regular alternation of numerous lines or bands of red and green color having their direction parallels to the lines of the grating, so giving the same pattern as the grating on the window. And he says, what he's saying here is that if you remove the lens at different distances, the bands changed their color, but they stayed perfectly distinct and well defined, even though the grating was very far out of the focus of the lens. And of course, the change of color is just the particular wavelength that was coming into resolution. And that was not my name, but this was known, and he made this observation in the middle of the 19th century, and then it was forgotten for a very long time until the 80s and early 90s, when mathematicians and physicists started working on it and called the revival of this grating pattern the Talbot effect. This was a name that Michael Berry gave to this phenomenon. He was one of the first people to study it. And in order to study this mathematically and to explain it, actually the explanation, if you pick the right equation to model this phenomenon, is not very technical. So what Berry and collaborators did in the early 90s, probably late 80s, is to model this phenomenon by the linear Schrödinger equation. I'll show you what it is later. And what they did is, supposing that the period of the grating is A, so these lattices are repetitive patterns, so they have a period. And let's suppose this period is A, and the wavelength of the light is lambda, so fixing just one color, if you want, in the light, one wavelength. He proved that the images that Talbot's sun actually form, they form at a regular multiples of a specific distance, which is a square over lambda, which is he called the Talbot distance. And what he did, if you model the grating, not the rating, the grating as a periodic initial data. So you give a 1 where there is a passage of light, and a 0 where there isn't passage of light. Then at the rational multiples of this distance, so either at this distance or at specific places, these fractional Talbot images consist of Q equally spaced copies of the grating, which superpose coherently when they add up, where Q is the denominator of this rational number. In any case, if you have a very precise description of this that was first given, and the interesting thing, well, it was then this effect was reproduced in much more modern experiments. This is one of them, and I have put down what exactly the 0, 1 that I mentioned in the previous slide are. So where this is just a grating made by just small slits where you allow light to pass, and intervals which are blocked to light. So where the light can pass along this periodic interval, you put a 1, otherwise it's 0, and that models your initial condition. And then you model the diffraction of light by the linear Schrödinger equation. This is the kind of pattern that emerges. So after at the full distance a square over lambda, you see that the same pattern that you had at the beginning is exactly reproduced. But at other distances that are maybe half of it or a quarter of it, you don't have exactly the initial pattern, but some superposition, some multiples, some copies of it. Okay, this, for example, is just shifted by half, where it was the light is in the middle of the dark, where it was dark at the beginning. Okay, this is at half distance. And so this has been reproduced experimentally and mathematically completely clearly. And there are other physical observations where this phenomenon appeared. And in this in this other observation, which are about the revival of electron wave packets in certain atoms, it was called quantum revivals. So revivals is another name that has entered now the literature for this kind of effect. And in this case, you have to substitute what? So the distance becomes a time, and it's the time in the evolution of the wave, and the periodic coordinate across the grating was when it becomes an angle, and the wave, the initial condition becomes the initial electron wave packet. And there are many review articles about this, and there is a very nice one in Physics World that, I mean, you will have the slides afterwards, so you can go in and read. There are many historical facts about it and a lot of pictures of these quantum carpets. But it's a similar kind of effect. This reproducing at certain fixed distances, something that looks very similar to the initial condition, or it's certainly a revival of the initial condition in some sense. So exactly what sense? So let's see exactly what, how Berry and others reproduce this mathematically. And I've given this as an equation in time and space. So it's really more about the quantum revival than about light, but it doesn't matter. It's the exact same mathematical description. So this is the linear Schrödinger equation. You here, well, it's the wave packet, it doesn't matter, but t is time, x is space, and periodically it's periodic in space. I've given the periodic interval is minus pi to pi. This function here is just the function that represents this alternating 1 and 0, but it's just 0 when x is negative and 1 when x is positive. So there is only one slit, one jump, okay? And then this is just the periodicity conditions. And if you study this, as Berry did, and as I will indicate a little bit, you find, first of all, this revival, this Talbot effect. So at any rational time, so any time that is a rational multiple of the initial period, which is 2 pi. So p and q are integers, and 2 pi is the period. So at any time that has this form, the solution is just a finite superposition of translated copies of this initial step, initial condition, which is 0 when x is negative and 1 when x is positive. So in particular, this means that if the initial condition has a jump discontinuity, like this one has, because it's 0 and then suddenly it becomes 1 without joining up, then the solution at these particular special values of time also has jump discontinuities. There is a specular effect at times that are not rational multiples of the period. At these times that are in some sense generic, because to hit on a time that is of this form, you really have to look for it. At other generic times, the solution doesn't have these discontinuities. It is continuous, but it's nowhere differentiable. It's continuous, but very rough. So exactly what does it look like? So these are just numerical computation. This particular ones have been produced by my current PhD students, George Farmakis, but there are many others. It's not difficult to produce this, okay? So here is my initial step function. And here you have a blue line for the real part and a red line for the imaginary part of the solution, because the linear Schrödinger equation is a complex valued solution. So the real part is 0 when x is negative, or here it's been shifted, it doesn't really matter, and 1 when it's positive. So it's a step function, 0 here, whereas the imaginary part is always 0. And if you compute the solution at these special values of the time, and here I have a couple of examples, you see that the solution is a step function, or many. It's, as we say, it's certainly very regular, and it reproduces the initial shape of the solution in many copies of it, translated and shifted, both in the real and the imaginary part. It's absolutely regular, and it comes from the initial condition. At generic times, the real part and the imaginary part look something like this. So very much rougher, but continuous. So very oscillatory functions that are continuous. It can be proved that they are actually continuous, but very, very regular. So there is this dichotomy between rational and irrational times, which in itself is quite a surprising effect, mathematically speaking. And it's exactly, so you don't see this really, if you look at the solution, this just seems a mess, but suddenly at these special times, it quantizes and becomes very regular. This is another example. These pictures were produced by my former PhD student, now collaborator, David Smith. He started, instead of starting with that kind of step function, he started with a very thin box. So this function is 0 almost everywhere. It's only 1 very close to 0. So ignore the vertical lines. It's just a step function again. And again, you can see that if you compute the solution of this problem at rational times, you get the revival of this shape in different places in both the real and imaginary part. But if you compute it at a generic time, this revival is destroyed. The pattern of discontinuities is destroyed. The function is continuous and very irregular. Okay, so here I come to how I got involved or interested in this problem. About 5 or 6 years ago, I attended a talk by Peter Olver from the University of Minnesota, and he was talking not about this equation that had been studied by Barry, but about another dispersive equation, one that I happen to have studied extensively for other reasons, the Airy equation, which is this one here. It's very similar. It's a time evolution, in which the energy is dispersed. And he was writing a book on PDEs, Peter was, and he was just trying to find interesting exercises for this book. That's how he told me the story. And so he thought, okay, because this is quite easy, if you give as a starting condition the step function that I used earlier, so something that's 0 for half of the interval and 1 for the rest, it's very easy to give an exercise. You can compute the Fourier coefficients, so a certain representation of this initial condition very easily. So it was quite a nice exercise to give to students, undergraduate students that are learning how to compute solution of periodic problems by using Fourier series. So he thought he would plot the solutions just by truncating the Fourier series of it and see what happens. And the first plots look like this. So you start with a very clear and structured solution, which is 0 or 1 and no other values. And if you let the evolution take over, according to this equation, the solution looks nothing like this. It's continuous, and it's very oscillatory and irregular. So two things, this discontinuity disappears, it's smoothed away, but the solution looks very irregular and very non-differentiable. So you cannot define the tangent to this curve anywhere. And then, I don't know why, because he didn't know the Talbot effect at this point. He computed by chance the solution at pi over 2, and this appeared. So very different. And then he started and tested it against a lot of other multiples. And as you can see, these are several multiples of the period 2 pi, all rational multiples, and the solution clearly suddenly remembers the shape of the initial condition and reproduces it in some sense. It again has discontinuities, and it builds up just with copies of the initial step function. So this is not it's a real valued PD, is not the linear Schrödinger. It models different physical phenomenon, but this effect is still very clearly present, and it's not very difficult to show why and how. And Peter did this. As I say, it's almost an exercise using Fourier series. Although, given that these solutions are very non-irregular, so they don't have a lot of smoothness, in what sense this series, this is for the mathematician, in what sense this series represents the solution is certainly not pointwise, it's just in a sort of quadratic average sense, but you can still write it and make rigorous sense of it. So there is a well understood procedure for writing the solution to this problem for this area equation. And for those for the mathematician in the audience, really the crucial fact is that the fact that this problem is periodic with respect to x forces periodicity also in t through this exponential, and that's really the core reason for this effect to happen. Anyway, this is just to say you can take this area equation again, start with the same step function as before. You can compute the Fourier coefficients of this explicitly without much difficulty. You can write down an expression that looks tame enough. You can truncate this infinite series at a large number. In fact, you don't need very many terms, and plot it and see what happens. And this is how Peter obtained his graphs. And you can not show the fractalization, so this irregularity and non-rational times, but at rational time you can prove then through this that the Talbot effect and this revival of the initial condition or dispersive quantization happens. As I said, you cannot prove just looking at the Fourier series the fractalization, and because when you compute using Fourier series a function that is not continuous and differentiable, there are this artifact, it's called the Gibbs phenomenon, that appears. So you can see, although this function should be just a step function, so completely constant here, and discontinuous, in reality these functions cannot, this representation cannot achieve that. It will sort of try to approximate the step with a continuous oscillation, which is this. This is the zoom of one of these discontinuities where you can see something happening. So you might think, well, this effect of irregularity at other times maybe is just an artifact of this Gibbs phenomenon. And in fact, if you try to use Fourier series to plot the solution at times that have bigger denominators, so where you should see a lot of copies of the initial condition, it really looks a mess, just as for irrational time. So is it, which shouldn't be the case. We know that it shouldn't be the case. We don't know just using Fourier series how irrational times behave, but it should not be a continuous function. It's not enough. It doesn't give enough resolution to see that from the pictures. Okay, so, sorry, what happened? Yeah, this is, for example, a solution at irrational time, and it doesn't look very different from this solution at a rational time with a high denominator. Here is 514, the denominator. So what, even, how can we make progress and extend to different PDEs to understand this effect. And in 2017, in 2016, this Erdogan and Tsirakis found a different way that really makes it clear the connection between this periodicity in time and the modularity and number theoretic properties of this exponential by writing a representation of the solution valid only at these rational times, that it's actually just a finite sum with the coefficient, these coefficients given by these exponential sums that are very well known in number theory. These are just Gauss sums, and the fact all sorts of very elementary but very profound number theoretic reasons come into why you can write it, this sum like this. And using, if instead of using this approximation by Fourier series, you use this exact finite representation to plot your solutions. Yes, this is what I was saying. These are Gauss steps, and it gives one nice thing of this representation is that, as you can see, the solution at this time is just given as a finite sum of values of the initial condition. U0 is the initial condition at some other points. At the many points that, so the solution at this time depends only on a finite number of values of the initial condition, which in itself is quite surprising if you've been working in dispersive PDEs. And this is what I'm saying here. You can just read off this representation that the solution depends only on a finite number of values of the initial condition. So in particular, if you are looking, if there are discontinuities, a finite number of discontinuities will appear at these rational times. It does not happen what happened. It does not say what happens at irrational times, but actually we know, because there has been other work to prove that at these other times, regularity is improved and the solution is continuous. And there is this fractalization. I'm not going to go there, it's much more technical, and I will just continue to focus on what happens at rational times. Okay, so if instead of using Fourier series to represent your solution, you use these exact finite representations, this is what you see. You see very clearly this step function. The vertical lines have disappeared because this is an exact representation, it's not an approximation, and it shows these jumps very, very clearly, even for this, for very high denominators. Okay, you can see this is the solution obtained by truncating the Fourier series. This is the solution obtained by just plotting this exact representation, and you just see you started with a step function at this time, which is 2 pi over 978 in this example. There are just very many tiny little segments and jumps in between. Okay, so this is a very startling representation of this effect. This is where quantization really comes into its own. And you can see that then this phenomenon of passing from this small but very jumpy functions that are discontinuous to a continuous one has nothing to do with Gibbs phenomenon. Is a properly number theoretical regularizing, dispersive regularizing property. Okay, so this is what was known when I started looking at this and was very intrigued. And this is just in summary. So linear dispersive PDEs like the two that I've shown, linear Schrödinger and Airy, which both are actually equations that come from physics for modeling, that are in physics usually with a nonlinear term, and I'll come back to that, to model various wave propagation phenomena. So they're not just mathematical artifacts, they're physical PDEs. And they all display this dichotomy in the solution behavior. The solution knows at what time you're computing it. If it's a rational multiple of the period, this quantization happens. And if it is not, it doesn't. If it is not, the solution is a bit more regular than the initial condition. So there is a regularizing effect, in particular on any initial discontinuities, but it's a general regularizing effect. The solution is slightly more regular than the initial condition. And as I said, the irregular oscillatory behavior at generic times is not numerical, is not an artifact, is not due to anything like bad approximation, but is a real regularization property of these particular PDEs. So all of this applies for these PDEs that when you look at the periodic problem. And it has been studied since Talbot quite a lot. There have been a lot of very high level and not so high level physical, phenomenological, and mathematical results about this. I'm not listing them all, but it has been an effect that since it has been revived by Berry in the 90s, had been studied extensively. Okay, so I was there listening at this talk, and the area equation is something I had worked on a lot because it's a third order problem, and these problems are not self-adjoint. They do not share a lot of the nice symmetry properties of second order problems, and in particular depend very sensitively on what boundary conditions you give. So I knew a lot about this linear equation, and I was intrigued by this property of the periodic problem. And my first question to Peter when I attended this talk was, is this really just true for periodic? At the time, I didn't really understand. What about if you have different conditions that are sometimes more physical, something like a zero condition, for example, that mean that you know that a wave is at rest at the end because, or something like this, I see. Or other PDEs, for example, PDE that might not have a polynomial dispersion relation, and there are many PDEs in physics that describe wave propagation problems, but are not of this type. And I was also curious to know if this effect is a linear effect. Is it appears only for linear problems, or maybe if you look at least at integrable nonlinear, or maybe general nonlinear PDEs that underlie these linear ones, it's still there or not? These were all open problems. And actually, what exactly is this revival property? What can I expect to find? So I will try to tell you what we have been doing since 2016 on this. And here I'll have mostly pictures. Okay, so this is probably the one with the most words, slide with the most words I have from now on. So the first result was pushing a bit the boundary of this validity was by Peter and Dave, my former PhD students. I put them in touch, and David had worked on the area equation and said, can you look at this? And they proved something for slightly more general boundary conditions. So not periodic. Periodic would have these values beta 0 and beta 1 equal. But if you have allow them to be different, then you can prove something. At least when you choose beta 0 and beta 1 such that the eigenvalues of the space problem are real. So even if it's not self-adjoint, you can still see revival. And they had some partial results about this, but also it was very exciting to see these, because these kind of boundary conditions appear in physics all over the place, but in particular, there are recent results about something called the vortex filament equation that they couldn't explain, that exhibits this kind of pattern and regular pattern revivals, but can be modeled by boundary conditions of this type. And so these are some examples, and you can, in the picture, it's clear that this rational multiples of this special Talbot distance is not quite the same because this is, I don't have, these are taken on an interval of length L, so it looks a little bit different, but the picture clearly shows that there is revival, and these are all for the case that the boundary conditions make the problem self-adjoint. But even for boundary condition for which the problem is not self-adjoint, you still see this revival. So being self-adjoint is not important, really. And when I started working on this, I wanted to try and understand this more generally. And in particular, all these pictures are, again, produced, and all the partial proofs they had were produced by Fourier methods. Okay, so we wanted to reproduce, first of all, the more compact and insightful finite representation of solutions, even when the problem is not entirely periodic. So that's what we did. We defined what we call the periodic revival operator, which is just this a sum with this Gauss, this particularly Gauss sums as coefficients. We just called it the revival operator of order L. It depends on the particular rational multiples that you're considering. But once you define this, you can express the solution of periodic problem for either the linear Schrödinger equation or the area equation just through, this is just notation. It's just a compact way to express the solution of either of these two examples, or if you want, a higher order ones, okay, through these finite sums that of a very special type that I have, that I have up here, okay, these very specific sums. And this is just a translation operator. It says that I evaluate f at x minus this point here, and which is exactly the same formula as Erdogan and Siraki said, just a rewriting. But now that we have this compact writing, and for all of you in the audience, sometimes mathematics is all about choosing them, well, not all about, but it's very much helped by choosing the right notation in order to simplify the situation and throwing away the inessential details to see a result. Then you can reconsider the same problems that Peter and Dave had considered and prove that at rational time, the solution of these boundary conditions with this beta 0 and beta 1, which we call pseudo-periodic boundary condition, is just really given by the sum of 4 periodic problems with slightly different initial conditions. So that's the original initial condition, and these are just reflections of it. So if that's the initial condition, you just reflect with respect to the center of the periodicity interval. But it's just a sum of 4 periodic problems, and that's all you need to know. Because if you have periodic problems, then you know that you have revivals. This is the proof of Berry. Okay, so that is a very compact and way of reproducing a known result. This was known, fine, but actually having this notation, and this also allows us to prove that there is also fractalization and smoothing at generic time, because all the known results for periodic problems can be translated to the pseudo-periodic one. It was also crucial to understand what happens for the third order problems, where actually things are not quite so clear. Okay, so we considered this just slightly changed. So this is not periodic, it just has one and the same modulus 1 multiplier on both the condition on u and on ux and ux and uxx. There are 3 conditions here. This is third order. And it seemed that in this case, then we didn't have revivals unless not just the time was a rational multiple of the period, but also this number theta here was not rational. So we needed theta to be rational, not integer, rational, in order to see revival, which was surprising. It was the first, quasi-periodic is almost periodic. It's certainly for the Schrödinger equation, it's the same behavior happens, but not here. And we were able to use our machinery to prove why this is the case. And the reason is that you can write the solution of this problem for the area equation, which is third order, by recasting it as a problem for the Schrödinger equation, second order, at a ration, but with a different initial condition. So the solution at a rational time for Airy is some translation and multiplied by some exponential, but it's the solution of the Schrödinger problem at a non-rational time. Because if this theta is not rational, it's not a rational multiple of 2 pi, then, so if this is not rational, then this is an irrational time. And we know that at an irrational time, the solution of Schrödinger is irregular, is not discontinuous. It does not exhibit revivals. And so this was once we had the right notation in time, we could prove this. And here are the pictures. So this is for the Airy equation, quasi-periodic, with this parameter theta either rational or irrational. So if this is, but always at rational time, so always at rational multiples of the period. Okay, so if theta is rational, revivals. If theta is not rational, oops, here, no revival, there, even though the time is rational. Okay, this was surprising to us. So the boundary condition, even when they're very close to periodic, really affect this completely. So this periodicity, which translates into a number theoretic property, is crucial for having this dichotomy and this at these specific times. We then looked at something that is physically even more relevant, type of boundary conditions that couple the solution and the derivative. These are called Robin type problems. And we could prove that there is not revival in the same sense as the periodic problem, in the sense that the solution is not just given by the initial condition translated and superimposed several copies of it. But it's still true that the solution at rational times or at irrational times behaves very differently. And in particular, it revives discontinuities at rational time, but not at irrational time. So do we call this revival? It's not quite so startling, but certainly the dichotomy of behavior is still there. So maybe it's some sort of weaker revival. We'll come back to that. The important thing is the level of regularization that the solution achieves at different times. So for irrational time, it's much more regular because it's continuous than at rational times where the discontinuities appear. Okay, this is just the expression. So again, what I just said, the initial discontinuities are propagated. So this is a weaker form of revival. And I'm only, okay, let me see, how much time have I got? 10 minutes. Let me rush through it just to give you some other examples. So we looked at very different type of equations that are not polynomially, do not have polynomial dispersion form. This was one, still a wave propagation equation, or the linear part of one. And we start with the same step function. We can write down the solution in the Fourier way because because this is linear and we can do that. And here are the pictures. Okay, so if you start with that step at rational multiples of the period, the solution looks something like this. It's certainly not a step function, but it has these cusps that really should extend. These are infinite cusps. Mathematica couldn't picture them as infinite, but they are infinite. And at different times, there are also these points where there is a jump. So there are both jump and discontinuities at rational times. Whereas at irrational times, it's the same type, different type, but a wiggly mess, just as before. So there seems to be a revival property here too, but it's not certainly of the same form. And to cut a long story short, we did work on this. We expressed the solution in terms of certain special functions, which are depicted here. And so these are the basis for our finite representation of the solution. They are either they either have discontinuous jumps or these infinite cusps. And what we found after some mathematical analysis of it is that for this problem, the solution to the periodic problem is a linear combination of translate of the initial condition, just like before, and translate not of the initial condition, but of the Hilbert transform of it, which is the transform that appears in the definition of the PDE. So it's not quite the same as before, but it's almost, because this is the solution, and it's given by these delta functions, we give discontinuities, and cotangent functions that give the Hilbert transform. That, in any case, it has a very regular form here too, despite the fact that we completely lose the usual Gauss sums. So these are sums that are obtained using a very different type of special functions. So that was quite nice and quite surprising in some sense. But what's even more surprising is what happens for when we looked at nonlinear problems. All the things I've spoken about until now are linear. It was interesting to check because all these linear PDEs are just the linear part of important nonlinear models in mathematical physics. Things like the nonlinear Schrödinger equation, the KdV equation, and all, which are both integrable, also other nonlinear problems like the quartic KdV that are not. The problem with understanding what was going on is that it's very hard to do numerics with discontinuous initial function and solution for these. So there were some initial numerical studies, but they could only run for small times, and they were very non-robust. So what happened to help us was that a new numerical methods were devised by a colleague of mine. Now she's moved to Katerina Schratz, who is now in Paris, that allowed us to make really very robust numerical computation. So here they are for the nonlinear case. Okay, so this is nonlinear Schrödinger, a box initial condition, and you can see, again, it's not quite the same box. It has some funny wriggles, but there is definitely revival. And the same for KdV, which is a third order nonlinear problems. It gets a little, and this is not just Gibbs phenomenon. It's really some slight some perturbation of the revival property, but this strong effect of the linear part is still there. One could argue that maybe this is because these are nonlinear, but weakly nonlinear. They're called weakly nonlinear. So the nonlinear effect really is relatively weak. But actually, this happens for also things like this, affine initial conditions, not quite. You see that it continues to be revived at rational times. And even for much stronger nonlinearities, this is still present, okay? And this is very, very surprising. It doesn't have anything to do with integrability. It doesn't have anything to do with nonlinearity. We understand now, and it's work that Erdogan and Sirakis have done, and we have extended, that the linear part drives the lack of regularization, and so drives the persistence of these continuities in the solution, and the nonlinear part cannot kill these discontinuities. It has a regularizing effect, but not regularizing enough to kill the discontinuities at rational time. And it's also true for the full Benjamin-Ono equation, of which I looked at the linear part first. Now it has also a nonlinear part. Again, if you start with a box condition, something very funny happens at rational periods, rational multiples of the period. So just to finish it seems clear that this dichotomy that we call Talbot effect of revival property or dispersive quantization is a very strong effect that is still valid when you perturb the boundary conditions a bit, but not very far from periodic, although we have now some results for general Robin condition that indicates that you still have an echo of the periodicity as soon as you are on a finite interval. So it's a very strong effect that really persists when you change boundary conditions, when you change and consider all sorts of different dispersions and even nonlinearities. So the defining characteristic of this effect is that generically discontinuities are killed and smoothed away to have a continuous solution at a generic time, but they are propagated if you look at this special value of the times, and there is no smoothing at this special value of the time. So this dichotomy seems to be a way to define the general revival property, weak in a weaker sense than just having an exact revival of the initial condition. And this really echoes the very nice title of one of the early papers on this effect by Kapitansky and Rodniansky that were looking at the quantum revival and the linear Schrödinger. And their paper was called, "Does a quantum particle know the time?" And I would paraphrase that to say, does a periodic dispersive wave or quasi-periodic dispersive wave know the time? And with that, it seems that the answer is yes, and I will leave it with you. I am not going to show, but if you take the slides, there is a whole list of the papers that I have either quoted or not quoted, but used to prepare this presentation. So thank you very much.
Thank you, Beatrice. Well, we'll be looking to get some questions from the audience. But in the meantime, I have a couple of questions. So you've considered, you've discussed quasi-periodic boundary value problems, right? Evolution, yeah. Quasi-periodic problems, say for the Schrödinger equation, for the Airy equation.
Yes.
If I think about the quasi-periodic problem as the result of the Bloch transform of a problem in the whole space, right? I could do it that way. Would the information that you extract about your solutions would give us some kind of information about the solutions on the whole line in X?
So I sort of don't think so, because this is really, you can take the period to infinity in some sense, but you completely lose this dichotomy then, and these revival operators really only make sense on a finite.
Well, no, I don't want to take the period to infinity. I want to, imagine that you have a periodic coefficient in front of your the spatial part of the operator. Yeah. Let it be smooth. Will you have also Talbot effect for that kind of problem?
I don't know. It's a good question that I will have. I need to think about this.
Because then I can ask the same question that I asked a minute ago about a problem with the periodic coefficient.
I understand. Yes, I understand what you're saying. Certainly, there is a dramatically different situation for the second and third order problem, which I, in some sense, expected, because the third order problem is very different when you have boundary value problems, and even half line. So half, not the full line, but half line it's completely different, the behavior of a third order and of a odd order or even order problem. So I expected that, but whether it will give us some, I will have to think about the question that you are asking, which is slightly different.
Okay, thank you. Sorry, there is a problem with my camera. I'm trying to switch it on and it tells me that there is an error. Right, so I'm looking at the questions. Okay, so there are some first questions coming. So if we think about the physical application to light propagation, will the Talbot effect also depend on the magnitude or just phase?
So it depends on the wavelength of the particular light that you're looking.
So I guess if it's a linear wave propagation, then the amplitude.
Yeah, but this we're talking about linear. I mean, these are those experiments were all in free space. So no.
Then the next question is, what happens if incident angle moves? So, I mean, if you change the incident angle, right?
Yeah, so actually that's Talbot did a lot of that, trying to change the angle of the lengths, or which is, you know, the same in a sense. And you change the length of where this periodic grid it's repeated, but you still have this effect.
Will it somehow also depend on the whether the tangent of that angle is rational or irrational, or?
So that it depends. Not for the Schrödinger problem. No, not for light. It would for the Airy, if you could, in some sense, think of it as the same type of physical problem, which it isn't.
Okay. So the next question is, in diffraction gratings, so I don't know, why are diffracted patterns periodic in diffraction gratings? So I don't understand this question, so I'll try to think about it. So does Fourier analysis of the Talbot effect have application in signal processing?
So of course, everything that we actually compute is in some sense rational. So it's very hard to extract rational times from the continuous, so everything is. It's very hard in practice to isolate these special points. Okay. So this is a question I've been asked before, and I've thought about. And really, in terms of the applications, you would need to be able to discriminate between rationals and irrationals on the line or in the space. And everything I've shown, even when I say it's an irrational, really, it's a rational approximation to an irrational. So it's very hard to know how to do this. To some, you would need some sort of tolerance, probably, and it may be possible. But I don't think anyone has done it or thought about it deeply.
Okay. Do the diffraction patterns get smoothed for large spacings of adjacent diffracting elements?
So as long as you can model it as a periodic box where things happen, the spacing between the slits doesn't matter at all.
And how does the dispersive wave keep record of time?
Yeah, I don't know. It's well, maybe it's not really a real physical model. It's something that approximates it, that uses our own very symmetric way of thinking and the properties of numbers that we use. These are all number theoretical properties, really. The property underlying all of this is the fact that if there is modularity between certain numbers, say if two integers are congruent modulus m, then their square, their cubes, their powers will also be congruent modulo something. And that's fundamentally what's happening here. For the ones like Airy and linear Schrödinger, where there is just a polynomial dispersive relation, so just powers of these numbers. It's much more exciting for things like the Hilbert transform PD that I showed Benjamin Ono, where there is not, the dispersion is not polynomial, so it's not just powers like that. So it's much more difficult to see the relation with the number theory underneath. But it's still there. There are different, it's not exponentials, it's other special functions that play a role, but there are still.
There is a mathematical question: how does the Gibbs phenomenon occur? I guess that's a Fourier
that's
analysis
a very
question.
classical. So you're trying to approximate or to represent a function that has a jump with a sum of functions that are not just continuous, they are continuous and infinitely differentiable. So it cannot do it. It cannot quite do it. So it's very well understood what that sum represents, and it will represent something that kills the jump, but tries to be as vertical as possible. So we'll have little wiggle just to fit that smoothing within as small a space as possible.
But
it's not a hand-waving explanation, but it's due to the fact that you cannot use Fourier series to represent exactly pointwise functions that are not continuous and differentiable, that have jumps.
It's 19%, isn't it, of the jump? I think
something like that.
Yes.
Maybe 11%, but it's a 10%.
Maybe 11, yes. Can you recommend an introductory article or a review paper?
So there is this article that I gave the link to somewhere in the talks at the beginning in Physics World that has quite a lot on it. And there is also, I forgot, I don't know if I put it in my list here. There is a review article about the more recent mathematical, no, I didn't put it here. So I will add it by David Smith in like Quanta magazine or one of these. So I will send Jaime the link so he can provide it to everybody. And that's quite a nice review that explains in very non-mathematical terms the theory.
Okay, well, this seems to be it. Jaime, we don't have more questions, right?
Oh, sorry. No, we have regards from different parts, and also congratulations to Beatrice for the interesting presentation.
Thank you.
It has been it's interesting to see the mathematical complexities of this Talbot effect, well, the Talbot effect, as you commented at the beginning, is really surprising optical phenomena. Interesting that he was able to observe it at the time, because well, the devices he was using were not really good for observing this periodic repetition of the diffraction pattern. So I am really very interested in knowing more about this. And interesting that well, it's although it was discovered long time ago, it's still presenting open questions and challenges for the mathematical analysis, including your last question on the if a periodic dispersive wave can record the time. That's challenging.
Yeah, maybe it just says that we don't really understand what our models exactly say or represent.
No, well, thanks very much, Beatrice, for the very interesting conference and interesting studies. And thanks, Kirill, for taking the questions. I was noticing that we were using, we translated some of the questions, so we don't really convey the intention of the questions, but it's perfect. Thanks very much to all for the comments and the questions, and well, thanks again to Beatrice for the interesting conference.
Thank you, everybody.
And well, I don't know if Kirill wants to say something, or and we can also extend the invitation to join us next week, next Tuesday at the same time. We have a conference by Dr. Hidalgo Bastida from the Manchester Metropolitan University on biomaterials and regenerative medicine. So we are all invited to join us.
Okay, thank you very much. Well, let me thank Beatrice again for such an inspirational talk, and I'm personally curious about several questions as well. So, right. So with this, I think,
I will put in the chat the link to this article that I mentioned.
Right. Okay. Well, I guess someone can pass it on, right, to the participants.
Yes.
I'm not sure if the participants can get it directly from the chat.
Well, no, not really, but we will copy this paper and add it to the recording of the conference.
Okay, thank you.
Okay, thank you again. Thank you.
Bye, Kirill. Bye, Jaime. Thank you very much.
Oh, thanks again, and well, I hope we can meet soon in Edinburgh or in Mexico.
Let's hope so, or maybe Mexico City.
Okay, yeah, that will be perfect.
Are we off air now?
Yes.
Desde milenios atrás, el cáncer ha sido uno de los padecimientos más terribles de los seres humanos. Y a lo largo de la historia, la ciencia ha buscado entender qué es el cáncer y cómo curarlo. La ciencia avanza, y con ello nuevas propuestas y tratamientos surgirán, con la esperanza de que en un futuro cercano se logre ganar la batalla en esta larga lucha contra el cáncer. Por estas razones, la prevención juega un papel fundamental en el control del cáncer. Desde milenios atrás, el cáncer ha sido uno de los padecimientos más terribles de los seres humanos. Y a lo largo de la historia, la ciencia ha buscado entender qué es el cáncer y cómo curarlo. La ciencia avanza, y con ello nuevas propuestas y tratamientos surgirán, con la esperanza de que en un futuro cercano se logre ganar la batalla en esta larga lucha contra el cáncer. Por estas razones, la prevención juega un papel fundamental en el control del cáncer